production of a large diameter crane rope, rated for 160-ton lifting capacity, begins with high-strength steel wires drawn for exceptional tensile strength. These wires are twisted into strands, then helically wound around a steel core to form the rope. Precision stranding machines ensure uniform tension and diameter. Lubrication, inspection, and load testing follow, guaranteeing durability, flexibility, and reliable performance in heavy-duty crane operations. The 35 x 7 wire rope belongs to the multi-strand rotation-resistant class used for hoisting operations. Its 3-layer construction delivers high flexibility and stability under load, making it suitable for many types of crane systems installed on marine vessels. Inside the manufacturing facility of SMWorks lies a fully integrated ISO-certified production hub dedicated to high-performance industrial hose systems. The process begins in the hydroformed hose production area, where metal tubes are shaped using high-pressure fluid-forming technology. The next stage is mechanical hose production, where hoses are mechanically formed and processed to meet various industrial specifications. In the braiding production section, stainless steel wires are braided around the hose surface. This protective layer improves durability, heat resistance, and protection against external damage. After braiding, components move to the assemblies area, where skilled technicians assemble fittings, connectors, and hose components into complete systems. Another important section is bellow production, where flexible metal bellows are manufactured to absorb vibration and allow controlled expansion and contraction. The facility also includes interlock hose production, producing highly durable hoses designed for demanding environments. Before shipment, each hose receives identification through in-house laser marking facilities. Finally, the products proceed to packaging and dispatch, where they are securely packed and prepared for delivery to customers worldwide. Massive steel plates begin their journey on high-precision cutting lines, where raw material is trimmed and prepared for the next stage of production. The process sheets are then rolled into enormous steel coils, tightly wound for efficient storage and transport. From here, the coils travel to automotive manufacturing plants, where they are unrolled and fed into powerful stamping presses. These machines shape the steel into body panels, chassis components, and structural reinforcements. Through advanced forming, welding, and assembly processes, the once flat steel is transformed step by step into the essential framework of modern automobiles. Inside the production facilities of Rogue Fitness, massive steel coils are transformed into the structural tubing used to build heavy-duty power racks and strength machines. The process begins when large steel coils are loaded onto the production line. In some factories, coils must first pass through a slitting machine that cuts them into narrower strips. However, in this case, the coils already arrive at the correct width, allowing them to move directly into the next stage. The steel coil is placed on an uncoiler, which gradually unwinds the strip and feeds it into an accumulator. This section stores a long loop of steel, so the line can run continuously. When one coil runs out, operators weld the end of a new coil to the previous strip, preventing production from stopping. After the accumulator, the flat strip enters a series of forming stands. Each stand bends the steel slightly, step by step, until the strip begins to take the shape of a tube. The edges are precisely aligned as the material moves toward the welding station. At the welding stage, the tube passes through an induction coil that heats the steel edges. The edges are then fused together using electric resistance welding, ERW, creating a strong and continuous seam. During this process, excess metal known as scarf is squeezed out and removed to maintain weld quality. Next, the tube enters the sizing section, where additional rollers refine the tube to its exact dimensions. A high-speed cut-off saw then slices the continuous tube into precise lengths. Finally, quality tests such as flattening inspections confirm the strength of the welded seam before the tubing moves on to become part of Rogue's rugged gym equipment. Inside the advanced steel facilities of ProInvest Group, the production of chromist hard chrome-plated bars and tubes reveals a meticulous industrial process designed for high-performance hydraulic components. Raw steel bars and tubes first undergo mechanical preparation processes, such as peeling, straightening, chamfering, and precision grinding to achieve accurate dimensions and surface quality. Once prepared, the components move to induction hardening and continuous chrome plating lines, where a controlled chromium layer is applied to the steel surface. The plating process is followed by polishing and passivation, creating an extremely smooth surface finish, capable of withstanding demanding industrial environments. Strict dimensional inspections ensure each bar meets tight tolerances, with surface roughness reaching values as low as Re 0.20 micrometers and chrome layer hardness exceeding 900 HV. After finishing operations, the bars and tubes are cut to length, packaged, and prepared for delivery to customers worldwide. Handling massive volumes of cooling water inside a power plant demands machinery built on an extraordinary scale. The 71 APM vertical circulating water pump represents one of the most powerful solutions engineered for this task. Capable of moving water flows reaching 170,000 cubic meter per hour through a massive column structure exceeding several meters in diameter. The assembly process begins with the outer column and suction bell, which form the submerged intake section of the pump. This large bell-shaped inlet guides incoming water smoothly toward the impeller while minimizing turbulence and hydraulic losses. Once assembled, the suction bell and column sections are carefully lowered into position and aligned to ensure structural stability. Attention then shifts to the pumping element and diffuser bearing assembly. The pumping element contains the impeller and diffuser components responsible for converting rotational energy into controlled water flow. Diffuser bearings are installed to stabilize the long vertical shaft while allowing smooth rotation under heavy hydraulic loads. Next comes the installation of the pumping element into the column structure. Precision alignment is critical at this stage because even minor deviations can create vibration or excessive wear. The vertical shaft sections are connected through shaft couplings, forming a continuous drive line extending from the motor at the surface to the submerged impeller deep below. After the drive shaft is secured, technicians install the inner column or enclosing tube, which protects the shaft and allows lubrication of internal bearings during operation. The foundation plate and discharge head are then mounted at the top of the structure, providing the mechanical interface between the pump and the facility's piping system. Subsequent stages include the installation of the stuffing box, sealing components, and bearing housing, all of which protect the rotating shaft while maintaining operational stability. The motor support structure is assembled next, creating a rigid platform capable of carrying the heavy electric motor that drives the entire system. With the motor installation completed, the pump is connected to a specialized test loop, where engineers verify alignment, sealing performance, vibration levels, and hydraulic output. Only after comprehensive testing confirms full operational reliability is the massive circulating water pump ready for deployment in large-scale industrial cooling systems. The production of modern turbochargers requires an advanced combination of precision engineering, digital simulation, and strict quality control. At facilities such as those operated by Garrett Motion, the process begins with detailed product measurement and engineering drawings that define the exact geometry and performance targets of each turbocharger model. Computer simulation is then used to analyze airflow, thermal loads, and rotational dynamics, ensuring the design will deliver optimal boost pressure and durability. Once validated, molds for casting key components are machined with high precision. The turbocharger housing is manufactured through advanced machining processes, followed by online dimensional detection systems that verify tolerances in real time. Rotor shafts are machined separately using high-precision equipment, then subjected to multiple inspection stages, including online measurement and in-shaft verification. Each rotor shaft undergoes dynamic balancing to ensure stability at extremely high rotational speeds. After cleaning and inspecting all spare parts, technicians assemble the turbocharger core. The central rotating assembly, known as the CHRA, is dynamically balanced again before undergoing oil leak detection tests. Additional inspections verify the performance of electronic valves, actuators, and nozzle rings. Only after passing every test is the complete turbocharger approved for final performance testing and delivery. Every day, millions of heavy trucks move freight across Europe's highways, relying on precision components designed to endure enormous loads in constant motion. Production begins with forging, where bearing steel is heated to around 1,200 degrees Celsius before entering powerful presses that compress and shape the glowing metal into ring-shaped blanks. After forging, the semi-finished components are transferred to specialized manufacturing lines for heat treatment. Inside hardening furnaces, the rings are reheated to temperatures exceeding 800 degrees Celsius, then rapidly quenched and tempered. This process gives the steel its required hardness, while maintaining the toughness needed for long service life under extreme operating conditions. The next stage focuses on precision machining. Grinding machines refine the outer diameters and raceways with extraordinary accuracy, often within tolerances of only a few micrometers. Quality control is integrated throughout the entire workflow. Every critical dimension is measured, surface geometry is inspected, and finished components are permanently marked with laser identification codes for traceability. In the final assembly stage, rollers, cages, and rings are combined to create complete tapered roller bearings. After one last inspection, the premium X-Life units are carefully packaged, ready to support the demanding transport systems that keep global logistics moving. At the busy industrial hub of Port of Tauranga near Mount Maunganui, specialized steel fabrication plays a central role in supporting the expansion of large logistics infrastructure. The fabrication work involved producing heavy welded steel girders, designed to support a large-span structure supplied by Steltec. Once completed, the warehouse framework will extend approximately 300 meters in length and incorporate structural spans approaching 70 meters, creating a vast column-free interior space suitable for large-scale cargo handling and storage operations. Manufacturing these beams required precise cutting, plate preparation, and controlled welding procedures to ensure both strength and dimensional accuracy. Steel plates were first cut and assembled into girder sections before undergoing multipass welding to form rigid structural members capable of carrying substantial loads across long spans. Strict quality inspections accompanied each stage of fabrication, including weld testing and dimensional verification. The completed beams are designed to integrate seamlessly into the larger Steltec structural system, forming the backbone of the warehouse, roof, and support framework. This project highlights the importance of precision steel engineering in delivering large-scale port infrastructure capable of supporting growing freight and logistics demand. In the steel processing industry, precision cutting technology is essential for productivity and material efficiency. Developed by Lazary Group, the TL2200 layer cut system delivers powerful performance for high-volume steel fabrication. Equipped with horizontal and vertical clamping systems, the machine ensures exceptional stability during cutting operations, producing clean and accurate results. With the capacity to process layers up to 1,500 millimeters wide and 160 to 500 millimeters high, the TL2200 handles both solid and hollow sections with consistency. Large circular blades ranging from 0,1500 to 0,2230 millimeters provide remarkable versatility, making the system a benchmark solution for modern iron and steel manufacturing facilities. Nordis Fitness, one of India's leading manufacturers and exporters of fitness equipment. With more than 32 years of manufacturing experience, the company has built a reputation for producing a complete range of commercial cardio and strength machines. The journey begins with design and engineering. Every product starts as a detailed engineering drawing, created through advanced computer-aided design systems. With a fully equipped in-house design and research facility, the engineering team continuously develops new products while improving durability, performance, and safety standards. Once the design is finalized, production moves to the large manufacturing floor. Here, modern CNC automation systems ensure precision and efficiency throughout the fabrication process. One of the key machines used is the 3D laser cutting system, capable of cutting complex tube shapes and sheet metal profiles with extreme accuracy. These precisely cut components form the structural frames of gym machines. Next comes the machining process. Specialized equipments, such as fully automatic stack-weight drilling machines, produce up to 100 pieces per hour, ensuring consistency in every weight plate used in strength training machines. For more detailed components, advanced VMC machines are used to achieve highly precise cuts and smooth finishes.
Well covered with PE, face mask, leather jacket, gloves.
In addition to laser cutting, the factory also uses water jet cutting technology. This system can cut a wide range of materials without generating excessive heat, preserving the structural integrity of the material. After the metal parts are manufactured, they move into the surface treatment stage. First, components pass through an automatic sandblasting process that removes impurities and prepares the surface. Then, the parts undergo electrostatic powder coating, an advanced finishing process that provides a smooth, durable, and corrosion-resistant surface. The final stage is assembly. Skilled technicians carefully assemble the machines and inspect every component to ensure it meets strict quality standards. At the Wanju factory, the production of cast iron household items follows a carefully controlled metallurgical process that transforms raw metal into durable products such as pots, pans, and metal containers. The process begins in the melting department, where cast iron and alloy materials are heated inside large industrial furnaces at temperatures exceeding 400 degrees Celsius. Under intense heat, the solid metal becomes molten and ready for casting. Once the proper composition and temperature are achieved, the liquid metal is transferred to casting machines or molds. Molten iron is then poured into prepared molds designed to shape items like cookware and buckets. As the metal cools and solidifies, it gradually forms the basic structure of the final product. After cooling, the molds are opened and the rough castings are removed. At this stage, excess metal such as runners, gates, and flash must be removed. Cutting equipment and trimming tools eliminate these surplus sections, leaving the primary cast form intact. The components then move to finishing operations. Grinding machines smooth the surfaces and remove imperfections created during casting. Additional machining may be performed to achieve precise dimensions and improve surface quality. After inspection and quality control checks, the finished cast iron products are prepared for further coating, packaging, and distribution. High-volume cookware manufacturing increasingly relies on automated coating technology to ensure consistent quality and durability. An automatic PTF represents one of the up to deli. At the beginning of the process, each pan body is placed into a rotating fixture mold mounted on a continuously moving conveyor. These circular holders keep the cookware stable while allowing controlled rotation. As the conveyor advances, the pans travel steadily along the automated line and enter a precision spray chamber. Inside the chamber, specialized spray guns apply layers of PTFE-based non-stick coating in a controlled pattern. The rotation of the fixtures ensures the coating spreads evenly across the entire cooking surface and outer walls. Automated spray control regulates pressure, spray angle, and coating volume, minimizing overspray while maintaining consistent film thickness. Through synchronized conveyor motion, rotating fixtures, automated spraying, and controlled curing, the entire coating line operates as a seamless industrial system, capable of delivering high throughput, precise coating quality, and repeatable results in large-scale cookware production. Inside a modern strength equipment workshop, the production of premium dumbbells reflects a balance between industrial precision and traditional craftsmanship. Every stage of the process is carefully controlled to ensure durability, weight accuracy, and the refined finish expected in professional training facilities. The steel is transferred to powerful cut presses where immense pressure shapes the billets into the rough form of dumbbell heads. This cutting process is repeated precisely. After that, the semi-finished pieces move to CNC machining stations. Here, high-precision cutting tools refine the surfaces, ensuring the faces of the dumbbell heads are perfectly parallel and the central bore is machined to exact tolerances. Accuracy at this stage is essential, as even small dimensional variations can affect weight balance and assembly alignment. The handles are manufactured separately from hardened steel bars. These bars are cut to length and processed through automated lathes that form the grip profile. Knurling machines then engrave the familiar diamond pattern texture onto the handle surface. This pattern provides athletes with a secure grip, preventing slipping even under heavy loads or intense training conditions. Once both components are completed, assembly begins. The machined dumbbell heads are fitted onto each side of the handle and secured through high-strength welding on the design. Skilled technicians inspect alignment and symmetry to guarantee The finished equipment maintains perfect balance during use. The rubber mixture is then fed into a hydraulic molding machine. At the same time, the metal dumbbell core, consisting of a steel handle with two solid weight heads, is carefully positioned inside a dedicated mold cavity. This mold is engineered to match the exact shape and dimensions required for the finished rubber-coated dumbbell. Once the metal core is secured in place, the machine injects or compresses the prepared rubber compound around both ends of the dumbbell. Under high pressure and controlled heat, the rubber flows evenly through the mold, tightly wrapping the two weight heads. This automated process ensures a uniform coating thickness while firmly bonding the rubber to the metal surface. Quality control is integrated throughout the entire process. Each dumbbell is weighed and inspected to confirm it meets strict tolerance standards. Edges are smoothed, surfaces checked for imperfections, and markings, such as engraved weight indicators or brand logos, are carefully applied. The final result is far more than a simple piece of gym equipment. Through the combination of advanced manufacturing technology and skilled craftsmanship, each dumbbell becomes a precisely engineered training tool designed to endure countless repetitions, heavy drops, and years of demanding performance in gyms around the world. In heavy steel fabrication, forming large flanges requires immense force, strict dimensional control, and a carefully coordinated sequence of shaping operations. The process typically combines the power of an 800-ton hydraulic press with the precision of a 30-ton flange bending machine, allowing thick steel plates to be transformed into perfectly curved structural components. Production begins with the preparation of high-strength steel plates that will ultimately form the circular flange. Each plate is first inspected for thickness, consistency, surface defects, and mechanical properties. After quality verification, the material is cut into precisely measured segments according to the flange diameter required for the final assembly. Plasma or CNC cutting systems are commonly used to ensure clean edges and accurate geometry before forming begins. The first major forming stage takes place on the 800-ton hydraulic press, a massive machine designed to apply enormous vertical force. The steel segment is positioned between specially designed forming dies that gradually shape the plate into a curved profile. As the press descends, hydraulic cylinders generate tremendous pressure, forcing the steel to deform plastically without cracking or weakening its internal structure. This step establishes the primary curvature that will later define the circular flange. Operators carefully control pressure levels, pressing speed, and die alignment to maintain consistent deformation across the entire segment. In many cases, the pressing process is performed in several stages. Each stroke of the press increases the curvature slightly, preventing excessive stress concentration and ensuring the steel retains its structural integrity. Precision gauges and templates are used to verify the curvature after each forming pass. Once the primary shape has been achieved, the partially curved plate is transferred to the 30-ton flange bending machine for fine forming. Unlike the massive hydraulic press that provides brute force, this specialized bending system focuses on precision shaping. Adjustable rollers or bending arms gradually refine the curvature, ensuring that the flange segment matches the exact radius specified in the engineering design. During this stage, the machine applies controlled bending forces while rotating the steel segment through the forming rollers. This process smooths the curvature and corrects any slight variations left from the primary pressing stage. Technicians frequently measure the arc geometry, ensuring that each section will align perfectly when multiple segments are later assembled into a full circular flange. After bending is completed, the flange segments undergo edge preparation. The ends of each curved section are trimmed and beveled to create accurate weld joints. This preparation is essential for the later assembly stage, where multiple curved pieces are joined together to form a complete ring structure. Surface cleaning and dimensional inspection follow to confirm that tolerances remain within strict engineering limits. Quality control plays a crucial role throughout the entire forming process. Inspectors verify curvature radius, flange thickness, and alignment using specialized measuring tools and templates. Any deviation from design specifications must be corrected before the component proceeds to the welding and finishing stages. Inside the ingot department of Kaiser Aluminum at Warwick Operations, massive furnaces transform recycled scrap and pure aluminum into precisely engineered alloys for beverage can sheet. Molten metal is blended under strict control, then poured into advanced electromagnetic casting pits where powerful magnetic fields shape the glowing aluminum into enormous ingots. Some stretch the length of a school bus and weigh up to 44,000 pounds before continuing their journey to the rolling mills that produce the thin aluminum sheets used in food and beverage containers worldwide. The manufacturing of a stainless steel vacuum thermos flask is a complex industrial process that combines precision forming, welding, surface treatment, and vacuum technology. After this preparation, the pipe undergoes water bulging, a forming process in which high-pressure water expands the metal inside a mold to create the flask's characteristic curved shape. Once formed, the bulged pipe dividing step separates the material into individual flask bodies. The upper section then goes through neck spinning, where rotating tools shape the narrow mouth of the bottle. This is followed by rim neck cutting to refine the opening. The lower section continues with bottom expanding, shaping the base of the flask. Both the top and bottom parts undergo sizing and edge trimming to ensure precise dimensions. At this stage, outer bottom forming creates the external base structure that stabilizes the flask when placed on flat surfaces. Next begins the inner body making process, which produces the internal stainless steel liner responsible for maintaining temperature. Similar steps are repeated, including laser pipe forming, pipe ends rolling, welding seam flattening, and water bulging. The formed inner body is then divided and trimmed. Additional shaping processes, such as mouth beading and neck spinning, strengthen the bottle's opening and improve durability. To ensure leak resistance, the flask undergoes leak-proof forming and internal threading, which prepares the neck for screw-on lids. The inner bottom forming stage shapes the bottom interior before bottom edge trimming completes the structural adjustments. Cleanliness is critical before insulation is created, so the liner undergoes automatic ultrasonic cleaning. This removes oil, metal dust, and contaminants from the surface. The inner bottom welding process then seals the bottom of the inner liner. After welding, water testing verifies that the container is completely sealed. To improve vacuum insulation performance, copper plating is applied to the outer surface of the inner liner. Copper reflects radiant heat, helping maintain hot or cold temperatures for longer periods. The assembly continues with mouth welding, getter welding, and outer bottom welding, which connect the inner and outer shells together. The crucial step is vacuum suction, where air is extracted from the space between the inner and outer walls. This vacuum layer eliminates heat transfer through air conduction, creating the Thermos effect. After vacuum sealing, temperature measuring ensures that insulation performance meets required standards. The finishing stage focuses on surface treatment and appearance. The exterior first undergoes sandblasting to create a uniform texture. Next, electrolysis polishing smooths the metal surface and improves corrosion resistance. The mouth welding seam grinding step removes any visible welding marks. To achieve a premium finish, the flask passes through automatic CNC polishing followed by manual polishing, which refines the surface to a smooth shine. Finally, protective coatings are applied through lacquer painting or powder coating, giving the flask its color, durability, and resistance to scratches. Fabricating a 3-inch wire rope sling is a precise process designed to create a lifting component capable of handling extreme loads in heavy industrial operations. The procedure begins by selecting a high-strength steel wire rope that meets the required diameter and load rating. The rope is measured and cut to the specified length using hydraulic cutters to ensure a clean, accurate edge. After positioning the thimble, the strands are interwoven back into the main body of the rope through a process known as hand splicing or mechanical swagging. This step locks the structure together and distributes tension evenly along the sling. Finally, the sling is compressed or secured with steel sleeves, inspected for uniformity, and proof tested to ensure it meets strict lifting safety standards before entering service.